Yes, folks, how are you? Our previous session was the multiplexers, and now I'm going to want to look at the multiplexers today. Last thing we did was the two-channel multiplexing, and then you'd see that obviously now um, there we have on the board. All right, what I might have neglected to show was we have a symbol for this, and the symbol will simply be. Obviously, we have a select, okay? We have the one channel, we have the other channel, okay? And then we have a 2x1 multiplexer. We're dealing with the one that we have there, multiplexer, or we say max for short, okay? And our output is the one channel. Okay, this is 4-bit two channel, all right? It's two channel. It's a 4-bit per channel, right? This is, let's suppose this is A, that will be A0, A1, A2, and A3. And that will be B, the other channel, B0, B1, B2, and B3. Now that will be Z0, Z1, Z2, Z1, Z2, and Z3. Now obviously what it means is the select, if it's on 0, we get the one channel, and then if it's on 1, we get the other channel. All right, that is what I would like to mention before I go to the next thing. I said I will look at the demultiplexers. I just said I will look at the demultiplexers, but no. I forgot to mention. I think the videos become too long, and then some of those things just become too. You just become they become too excessive. You wouldn't want the video to be too long and then discuss a lot of different things in the same space. So what I want to look at, applications for these multiplexers. Okay, I'm going to look at the applications for the multiplexers, and I'll also look at the characteristics. All right, applications already said data selection. We select the one data using the switches. Remember, select the one data. I started off explaining this with the rotary switch, with the rotary switch, and we said that first I started with the two-way switch, what I call the single pole double throw switch. So this was just showing how you can select using switch from one input to another input, so you select the data that you prefer. Also data routing, we could decide which data we are sending through, more or less the route. Someone's called it routing, depends on which corner of the each corner of the globe you are. Some will say data routing, others will say data routing. And then operation sequencing, obviously you can see we are deciding how we what. You will see when you put in clocks and other different controls, that we could actually sequence our what, digitally sequence our data. We already explained in the when we bringing in the concept of multiplexing, how parallel data could be converted into what, into serial data. We could generate waveforms. We could decide that according to the high and lows, the outputs can actually be what, can be a certain waveform as per our desire. So we can generate waveform from this. Obviously logic function generation as well. Why? Because you saw how the switches are basically functions of some logic function or other. All right, some the combination of the what, of the inputs with those logic combinations, and we could obviously what, use that also to generate logic functions. Now also we have to look at the characteristics of the what, of the multiplexers. What are these characteristics? Let me move my board a little to there. Oh, I need that one there. Let me move my board a little there, so you can see that we already discussed the availability, where we say the 2 to 1 multiplexer, the 4 to 1 multiplexer, the 8 to 1 multiplexer, and the 16 to 1 multiplexer are the more abundant, are the more readily available what call this multiplexers, but we can combine them to get what, to get well, the last thing that I did was basically combine. last that I did was basically combined, where we did multi-channel or multiplexing is a basic concept, basic idea of combining. But also you could combine different size multiplexers to give you what? To give you a bigger range. If you felt that 16:1 was not big enough for you, you could combine and get more. Now parallel to serial conversion rate, yes, they remember that. Now we are looking at the characteristics now. Obviously, now if you are going to be switching from one set of data to another set of data, the conversion rate will also be very important. Okay, whether there's no, it doesn't delay too much. All right, the transfer accuracy is our data affected during this transfer. The data accuracy is our data thing. Now the throughput rate, are we what is the margin of error? What is the margin of error? All right, when we move from one data to another, what is the margin of error? All right, we also talk of the crosstalk as well. More or less, crosstalk refers to, sometimes you find that your outputs, some of the outputs give you something like inputs. When they give you outputs, you get outputs in instances where you don't really, you shouldn't be getting, so what you look at, the crosstalk there is whether to how much of a problem is this, like if you compare the true output to the what to the not so true output, what is the margin of what is the margin of error there as well. All right, logic functions have been discussed. Logic functions, basically, you've seen already that we're using the case there, the gate combinations, and you could see that basically our outputs were more or less some logic functions. I had an example where, for instance, we had a certain combination. Let's say I'll just use a basic one, S0 with S1, just those two. I had an example where, for instance, we got logic functions like, let's say, our D1 and D2. If it's two of them, they're going to give us 4, so I can't say and D2, I must say D3 and D4. And we saw that if this was the case, this here would come out probably here. I prefer D0, D1. It is clearer to say why it comes out where. Now, I don't want to make assumptions that 1 is necessarily that, but if it's 0, I know it must come out as 0 just by design. Now, this will be a 1 will be at the 1, a 2 will be at the combination that is 2, and the rest of it, by the way we say it, is nothing. So the only come out. Now, why would I say this is logic functions? It's because remember that this here can now work out to what? Not. This could work out to D0 and not D1 and not D2 and not D3. Okay, so this here is basically a logic function. Okay, so each and every one will have its own characteristic output there, and obviously these are logic functions, right? So now you then think of designing logic circuits from this. All right, so I just did the one example. You could go on and do the rest. Here obviously the D0 will be not, the D1 will be as is, the D2 will be not, and the D3 will be not, and all of them will be AND gates. All right, so these are logic functions. So we can derive logic functions from what? From these multiplexers. In any event, the building of the multiplexers themselves are already they have to have some logic circuitry with some internal logic circuitry. Now, that being said, I'm now gonna move on to demultiplexers. I've been threatening it's as if we are afraid of this demultiplexers. We've been threatening to do this, and we haven't really been arriving at that destination. Let's go on and look at the demultiplexers in our next session, because I think I've discussed a little bit too much on this session. You can read a little bit more on this. Probably I didn't put it the best way that it could be put. So probably look at this on your own and see where we get. I will look at the demultiplexers in our next session. I have a feeling that if I start them now, it will also be an extensive video. So then I will see you next. This shouldn't have been too long, but adding the DMX now will make it a little bit too long.